Today we're talking about maximum power transfer. Let me explain. Let me draw our famous squiggly box. All right, with all this talk about Thevenin and Norton equivalent circuits, modeling circuits, this is the perfect time to start talking about maximum power transfer. So let me pose the question to you. Given a source, what load can we attach to extract maximum power? Let me talk about this a little bit. The analysis is simplified by thinking of your source, no matter what it looks like, voltage, current, no matter what the resistance is, thinking about it as a Thevenin equivalent. So let me go ahead and draw that. We have a source here modeled by an ideal independent voltage source, Vs, and a series resistor, RT. And again, the question is, what load can I attach to this circuit such that we extract maximum power from the source? So let me go ahead and draw that. We'll call this RL for the load resistance. When you think about it this way, you know that no matter what's in this box, there's some source and some resistance associated with it. And it will turn out, we'll derive this in a second, that there is a single value of this resistance that extracts the maximum power. So let's just look at our load and start by saying, what's the power in that load? Well, we know that P load is going to be equal to the current in the load squared times the load. So P equals I squared R. We know this, and L just denotes the fact that we're talking about the load resistor. So if we wanted the power in a certain resistance, we know the resistance, so therefore we need the current. We'll look at our circuit, see that we have two resistors in series with a voltage source, so we can quickly use Ohm's law to figure out how much current is flowing here. This is easy enough. We have that the load current equals Vs, the source voltage, divided by the series combination of the Thevenin resistance or source resistance and the load resistance. Perfect. And with a quick substitution, we have that the power in the load is given by the source voltage squared times the load resistance divided by the square of the sum of the source resistance and the load resistance. Great, so now we have a nifty equation for the power in the load as a function of everything here in our circuit, our source voltage and our resistances, our source resistance and our load resistance. And this is great, but the original question was, what load can I attach here such that the power extracted or the power delivered to the load is maximized? And really the right way to approach this is just to treat this as this equation for the load power as a function of the load resistance. And when you look at it that way, it's easy to see how you can treat this function with a derivative. And then by setting the derivative to 0, we can locate the extrema, which I know has to be a maximum and not a minimum, because as you sweep RL, I know that the power can't go to infinity at 0 and infinity. I know I will never extract infinite power from this load. I know as I sweep RL, the load power has to look like this. There has to be a maximum somewhere. It has to be a maximum because if it were a minimum, then as I swept this resistance to either the low extreme or the high extreme, it would imply that I could extract infinite power from this source, which we know can't be the case, just intuitively. And you can also check with the calculus that you're indeed going to get a maximum. Anyway, let's carry on. What I'm going to do is take a derivative of this function, set it equal to 0, and then find the load resistance that satisfies that condition. And we will have our load resistance that gives the maximum PL. So let me quickly take the derivative. Let's see, the derivative of the load power as a function of RL, or with respect to RL, equals all this here. And we set it equal to 0. Great, and with a little bit of algebra, we can step through this, and then, therefore, the solution to this condition, that the derivative equals 0, gives us that RL equals RT. The load resistance that extracts the maximum power from this source is equivalent to the Thevenin resistance, or the source resistance. Maximum power transfer is achieved when the load resistance matches the source resistance, or Thevenin resistance. You might be thinking, well, how does this make any sense? How can it be a function of the source resistance? It's because of how I posed the original question. Now, you want to be careful here. I said that given a source, what load extracts the maximum power? And this is true. However, the absolute ideal optimum case, if you wanted a source to deliver the maximum possible power to a load, you would use a zero resistance source. Given that you have a resistance here, there's a certain load resistance that extracts the maximum power. But no matter what, this is still a resistance, and some power is dissipated here. You lose some energy to this source resistance. So you're not actually delivering maximum possible power, given that you have a certain voltage source. Not all of the power from this voltage source is going into the load. So if you had a certain load and you wanted to deliver maximum power to it, you would design the source with the smallest possible source resistance. And that's kind of a trick, duality, and it just depends on the semantics of how you phrase the question. The problem is that, it depends on the situation. A lot of times you're not designing the source. You're given a source, and you have to decide how to interface with it. And that's where all this comes into play. Anyway, I hope that was helpful. Let me know if I made any mistakes here, and let me know if you had any questions, and if you'd like to see anything else in the future. Thanks, and have a great day.